Heavily nested data. The 5 primitive types we've learned about are integer, float, boolean, string, and none. The 2 composite types we've seen so far are lists and data classes. These 2 new composite types are special because they are composed of other types. It's worth reminding you, data classes are not actually a type themselves, but a way of making new types. There are actually many more composite types in Python. But for now, we'll stick to these basic 7 types. In the earlier parts of this chapter, we saw how we could mix and match those composite types to make lists of data classes inside of data classes, and lists of lists. There's actually no limit to how much we can combine these different types. Let us look at a concrete example. Shown here we have 3 data classes, where 2 of the data classes have fields referencing other data classes. In fact, for the first level, the neighborhood data class's houses field is actually a list of the house data class. At the deepest point, there are 4 levels of nested data structure here. To quickly understand the structure of complex nested data, we find it useful to model the data in a class diagram. In the diagram shown here, we draw each data class in its own box. Then, we connect the related data classes together with lines. If the relationship includes a list, we draw an empty diamond starting from the owning data class. There is actually a lot more to class diagrams than what we have shown here, but this should be enough to get us started. As you process this complex nested data structure, you have to stay aware of where you are. This is similar to needing to navigate a maze. However, you also have to be aware of the tools at your disposal for accessing the data. When working with a list layer, you can either iterate through the data with a for loop, or index specific elements if you only need one. When working with a data class layer, you can only access attributes of the instance at that layer. In the green_acres example from before, if we wanted to add up the number of pets across everyone in the neighborhood, we would need to do an attribute access, followed by iteration, followed by a pair of attribute accesses. Here is an example function that counts the number of pets across all the neighborhoods. Notice that we have extracted the neighborhood.houses expression to a temporary variable first. We could have used the expression directly in the loop, if we had wanted to. We could also have broken up the house.owner.pets expression with some temporary variables. And we could have made a helper function to help count the number of pets in an individual neighborhood. Whether that is effective is partially a matter of opinion, but also a matter of how complex the code is. This function is not super complicated, so we did not bother breaking it up. But what if we had a more complicated structure? As previously mentioned, there are no limits to how much nesting can happen. Here we see a planner data class that has a list of day data classes inside. That day class has not only a date data class in one of its fields, but it also has a list of event data class instances. On the right-hand side, we have a list of planner instances making a very large example data structure. In this example, we define 2 functions, total_average and average_duration, with the goal of calculating the total average duration across multiple planners. Since this time, we had so many nested pieces of data, we found it quite helpful to break things up with helper functions. A good rule of thumb is that you should avoid having for loops directly inside of each other, unless you are working explicitly with a 2-dimensional list like we saw in the previous chapter. When we start dealing with truly nested data like this, we instead start relying even more heavily on functional decomposition to help us manage the complexity.